In the previous lecture, we have started to deal with the problem of semiconductor physics. And in this regard, you have seen an introductory lecture on semiconductor. Actually, you know, semiconductor is a material of great importance because today's solid state electronics is completely based on semiconductor. And in that introductory lecture, I have told you that basically semiconductors are of two types, and those are intrinsic or pure semiconductor, and another is extrinsic or impure, or you can say doped semiconductor. So before starting of the rigorous theory of this semiconductor physics, I would like to introduce you these two types of semiconductors. Actually, in two lectures on intrinsic and extrinsic semiconductor, we will see only the important properties of intrinsic and extrinsic semiconductor. This lecture is intended to deal with the properties of intrinsic semiconductor actually, and after that we will learn about the properties of extrinsic semiconductor. So now let us start to know about the intrinsic semiconductor, as we are going to see the important properties of intrinsic semiconductor. So some of the results in this lecture you will find without any proof, but that important results which I will write in this lecture directly, you will see its proof in our forthcoming lecture when we will start to deal with the rigorous calculation of these properties. Okay. So what is this intrinsic semiconductor? Actually, intrinsic semiconductor, as I have told you, it is also called pure semiconductor. So these are the semiconducting materials without any doping, without any impurity. Okay. And you have learned in the introductory lecture that in our periodic table there are 11 elements which have semiconducting behavior. But among those 11 elements, two are very important. And all the solid state devices based on this semiconductor are constructed by the use of those two materials, and those are silicon and germanium. So when silicon and germanium are in their pure crystalline form, they constitute actually intrinsic semiconductor. Okay. And as I have told you, when you talk about the pure intrinsic semiconductor, then no doping will be made in silicon and germanium. As you have seen in the introductory lecture, that the electrical conductivity of a semiconductor is controlled either by thermal agitation or by doping of some impurity atoms or by crystal defects. So this intrinsic semiconductor are materials whose electrical conductivity or resistivity is controlled by thermal agitation, only thermal agitation. Actually, increasing the temperature, you can increase the electrical conductivity of these materials. Okay. And when you talk about silicon and germanium, you can see these two materials are of fourth group of the periodic table. And as these are of fourth group, so these have 4 valence electrons. Okay. I have written here the electronic configuration of silicon and germanium. You know, silicon's atomic number is 14. So its electronic configuration is like this. And you can see the outermost shell, that is third shell of this silicon, contains 4 electrons. Okay. And that's why we say that this silicon is tetravalent. Similarly, the germanium has atomic number of 32, and it is its electronic configuration. And you can see that this fourth shell is the outermost shell or the valence shell of germanium, and it also contains 4 electrons. And so this is also tetravalent. Okay. So germanium and silicon both are tetravalent elements. Okay. So first of all, we will learn about the bonding between two atoms of silicon and germanium, that is the atoms of this pure semiconductor. Okay. You know that when there will be 8 electrons around an atom, then octet rule will be satisfied. So silicon or germanium actually must have 8 electrons for the fulfillment of octet rule, but these have only 4 valence electrons. So each atom of silicon or germanium must be surrounded by the 4 atoms of silicon or germanium. Okay. In fact, in actual crystal structure, the germanium or silicon crystal is just like diamond, just have diamond structure. And actually 4 covalent bonds are formed with 4 neighboring atoms, and these are directed along the corners of a regular tetrahedron, as in case of diamond. Okay. Actually, the silicon or germanium crystal therefore exhibits 3D regular network type structure. Okay. But for simplicity, I have shown here the 2-dimensional network to understand the bonding in this silicon and germanium crystals. Okay. You can see, if you consider this central atom of silicon or germanium, these 4 small spheres which I have shown in this figure, these are actually the 4 valence electrons of this silicon. Okay. And this silicon atom, or this, you can say this ion core, actually will form covalent bond with 4 neighboring atoms. So this is one of the neighboring atom, and it's one of the electron is this sphere, and a covalent bond is formed between this electron and this electron. Okay. Similarly, this is another neighboring atom, and its valence electron is this, and this will form another covalent bond. This is the 3rd neighboring atom, and with it this central atom form the covalent bond, and this is the 4th one. Okay. So in this way you can see that any silicon atom is bonded by the covalent bond with the neighboring 4 atoms. This is actually the 2-dimensional view of this bonds in silicon or germanium crystal. Okay. So these small spheres represent the valence electron, and inside this larger sphere we have represented the silicon or germanium atom. Okay. Now this structure is actually at a temperature of 0 Kelvin. When temperature is 0 Kelvin, then bonding in the silicon or germanium crystal is like as you can see in this figure. Okay. But when the temperature will be not 0 Kelvin but greater than 0 Kelvin, then there will be an important phenomenon. And what will be that important phenomenon? That is actually responsible for the electrical conductivity. Actually, when you talk about the temperature at 0 Kelvin temperature, you can see there is no free electron, because you can see each valence electron of any silicon or germanium atom is bonded together with the other valence electron of silicon or germanium, and by covalent bond. So there is no free electron, and if there is no free electron, then it cannot conduct electricity. So at 0 Kelvin temperature, due to the unavailability of free electron, this crystal, either germanium or silicon, just behaves like an insulator. Okay. Actually, for your convenience, I have mentioned all these things here. You can see it is obvious that all the valence electrons in silicon or germanium crystal participate in the formation of covalent bonds, and no electron is free to cause conduction, particularly at 0 Kelvin temperature. Thus, pure silicon or germanium behaves as an insulator at 0 Kelvin temperature. Okay? But what will happen when temperature is raised from 0 K? Let us see. Actually, when temperature is raised, these bonded electrons gain thermal energy. And when it gains sufficient amount of thermal energy, the covalent bonds will get breaked. But this breaking of covalent bond you can't explain on the basis of classical physics, because you know, according to classical physics, if two or more systems are in same physical condition and a perturbation is imposed on those, the final physical condition will be also same. So in accordance with classical physics, if any bond will be broken by thermal agitation, then since all the bonds were in same physical condition before heating, so all bonds should be break simultaneously. But actual situation is not like that. This is just a chance that any bond will break. Okay? And if the bond will break, electron will become free from the attraction of the parent ion core. So let us consider that this bond is broken. When this bond will be broken, let us see, then actually now there will be a vacancy at the site of this electron, and this electron will be detached from it. So this is actually the free electron after breaking of bond, free electron. Okay? And the position from where this electron get freed, that is there will be a vacant space by the electron, and that vacant space is actually called hole. And this hole just behaves like a positively charged carrier, positively charged particle. Okay? So in this way, due to thermal agitation, some of the valence bands, some of the covalent bonds are broken. According to quantum mechanics, it is possible. Okay? But according to classical physics, all the bonds should break simultaneously. But quantum mechanics says there is a probability of breaking of bonds, and that probability may be different for different bonds. So if you consider that this electron is detached, this electron becomes free from the attraction of the ion core of the parent atom and move inside the crystal randomly. So this free electron moves randomly inside the crystal. Okay? Now, another phenomenon also takes place. Now let us consider this is an electron which is in the neighbor of this covalent bond. And this electron then actually detached from its parent atom and forms here a bond. Okay? So now the electron which is detached from here, now hole will be created at this place, and again this electron comes to the vacant place, and again here bond is formed. So you can see as this electron moves randomly inside the crystal, the hole which was initially at this position, now it is at this position. So you can say that this hole is also moving randomly. Okay? And number of holes and number of electrons is same. Here you can see there is only one free electron and there will be then only one free hole. Okay? So in this way, inside the crystal now there are two randomly moving charge carriers. One is negatively charged electron and another is hole. Okay? So in this way, an electron-hole pair is created. EH pair is created. Okay. But in absence of any external field or voltage, the motion of the charge carrier will be random and no electric current will be constituted. But now let us consider we apply an electric field or voltage across this specimen of the crystal. Then what will happen? Then actually these charge carrier, that is electron which has negative charge, will experience an electric force just in the opposite direction of the field. So if field is directed from left to right, this electron will experience electric force from right to left. But at the same, this is electron, okay? But at the same time, this hole will experience electric force in the direction of this electric field because hole has positive charge, okay? So you can see that electrons and hole will experience electric force in opposite direction. Their motion will be in opposite direction. But what about the electric current? You can see, the conventional direction of electric current is just opposite to the direction of motion of the negative charge carrier. So the current constituted by this electron under the electric field will be in the direction of electric field. And current due to a positively charged carrier is in the direction of its motion. So current IH, which is due to the motion of hole, that will be in the direction of electric field. So both of these charge carriers, although move in opposite direction, but current constituted by them are in same direction. So the net current that will flow will be equal to IE plus IH. Here IE is current constituted by the electron and IH is current constituted by the hole. And in this way, the material becomes conducting. So you can see, due to thermal agitation, electron-hole pair is created, okay? And due to the motion of these under the external electric field, electric conduction takes place, okay? And here electron-hole pair is created, and when electron of the neighboring atom again creates the bond, then there will be annihilation of that vacant place. And so you can say that at the same time, recombination of electron and hole is also taking place. So there are two phenomena here. One is the creation of electron-hole pair and another is annihilation of electron-hole pair, which is called recombination. Okay? Actually, all these things we have understand here without considering the band model. Here we have only considered the bonding in these crystals. But the actual picture can be explained in more rigorous manner by considering the band model of the solid. So what is the band model of this pure semiconductor and how we can explain this conductivity on the basis of band model? Now let us see. Actually, what I have explained till now, I have mentioned here, I have written all those things for your convenience. You can write down these things in your notebook, because this type of question is also asked for particularly in short answer type in lower classes like B.Sc first year examination, okay, or +2 examination. I have mentioned here, you can see, as the temperature increases from 0 Kelvin, some of the valence electrons may acquire sufficient thermal energy to break their covalent bonds, okay, as I have told you, and become free from the influence of ion cores of the atoms. These electrons moves randomly in the crystal and are referred as conduction electrons. Okay. Each escaped electron leaves behind an empty space called hole, which acts like a positively charged current carrier. Okay. Thus, due to thermal agitation, an electron-hole pair is generated as shown in this figure. In this figure 2, you can see here actually electron I have shown here. The electron is detached from here. Okay, and hole is created here. Okay. Now, as I have told you, when a valence electron located adjacent to a hole, I have shown in earlier at this position, hole acquires a sufficient thermal energy, it may jump into the hole position to reconstruct the broken covalent bond. As I have told you that this electron jumps to this vacant place and again covalent bond is formed. Okay. These electrons and hole move in opposite direction under an external electric field and constitute electric current. Okay, I have shown here, you can see that the total electric current will be I plus IH, and electron is moving in the opposite direction of field and hole is moving in the direction of electric field, and IE is current due to the electron and IH is current due to the hole. And so the total current will be IE plus IH. Okay. Okay. Now, as I have told you that these things can be understood more rigorously and more clearly by considering the band structure of this material. Actually, in this figure, you can see the band structure of the pure semiconductor. Actually, in case of pure semiconductor, this band structure also depends on temperature. So here, first of all, we are talking about a temperature T equal to 0 Kelvin. Okay, T equal to 0 Kelvin. At T equal to 0 Kelvin, this valence band of a pure semiconductor is completely filled. This will be completely filled by electron. And this conduction band is completely empty. There is no electron in the conduction band at 0 Kelvin temperature. And these two bands, valence band and conduction bands, are separated by an energy gap which is called forbidden energy gap and or band gap, and the energy of band gap is Eg. You can see. Okay. So when you talk about the temperature of 0 Kelvin, as there is no electron present in conduction band, and you know if electron will be in conduction band, only the material will conduct. So at 0 Kelvin temperature, can this material conduct electricity? Answer is no. Why? Because at 0 Kelvin temperature, this conduction band is completely vacant, completely empty. And on the other hand, this valence band is completely filled with electron. Okay. So at 0 Kelvin temperature, this material just behaves like an insulator. Okay. This is just like an insulator. But what will happen? First of all, let us see. At this 0 Kelvin temperature, the band gap between these two is Eg. Okay. And the electron present in this valence band has not sufficient energy to surpass through this Eg. Okay. And so at 0 Kelvin temperature, the electron from valence band cannot jump to the conduction band, and so the conduction does not take place. But as the temperature is increased, let us consider temperature becomes equal to the room temperature, that is 300 Kelvin. Okay. Actually, even at room temperature, the electrons present in this valence band gains thermal energy. And if the energy gained by the electron is greater or equal to Eg, then those electrons will jump from valence band to the conduction band. Okay. And if an electron moves from valence band to conduction band, at that site in valence band, a hole will be created. So if, as I have shown in this figure, there are two electrons jumping from valence band to the conduction band, then there will be two holes in the valence band. Okay, if 3 electrons will jump from valence band to conduction band, then there will be 3 holes in the valence band. So you can see the number of electrons in conduction band. Let us say this is Ni, and this will be equal to number of holes in valence band. Let us say this is Pi. So definitely Ni will be equal to Pi. So we say that the concentration of concentration means number of electrons per unit volume. Similarly, concentration of hole means number of holes per unit volume. So in this pure semiconductor, the concentration of electron in conduction band and concentration of hole in valence band are always equal, because the number of electrons present in conduction band will be just equal to the number of holes present in valence band. Okay. In fact, at room temperature, what is the value of this Eg? In your textbook, you study that the band gap in case of silicon is equal to 1.1 electron volt. But remember, this value of 1.1 electron volt or 1.2 electron volt, which is mentioned as band gap in your textbook for silicon, that is not the band gap at all temperatures. Actually, band gap Eg of this pure semiconductor also depends on temperature to some extent. So the data given in your textbook is at room temperature, although in most of the textbook it is not mentioned that this is value of band gap for silicon, and this 0.73 electron volt is the band gap of germanium. At what temperature it is, although not mentioned in most of the textbook. But remember, these two values for band gap of germanium and silicon are at room temperature. Okay. When the temperature is 0 Kelvin, then the band gap of these semiconductors will be not equal to 1.1 electron volt and 0.73 electron volt. And when the temperature is much more than 0 Kelvin, even then this will be not equal to these values. So actually, experimentally it is found that the band gap of intrinsic semiconductor depends on temperature to some extent. So if you are talking about the band gap of silicon at a temperature T, its band gap Eg of T is given like this. This is 1.21 minus 3.60 into 10 to the power 4 into T electron volt. I have not derived this result, but as I have told you earlier, that these results will be derived, this will be discussed in more by rigorous method in our forthcoming lecture. Okay, I have written it here directly. Okay, so you can see this Eg depends on temperature, and with increase in temperature, as here there is minus sign, you can see the band gap will decrease almost linearly. Band gap of this semiconductor decreases with temperature T. Okay. And if you are talking about the temperature of 0 Kelvin, what will happen? When T is 0, you can see the second term will vanish and Eg will be equal to 1.21 electron volt. 1.21 electron volt. So actually, this value 1.21 electron volt is the band gap of silicon at 0 Kelvin temperature. But if temperature will be increased, and then you will see that Eg will decrease by from this 1.21 electron volt value. Okay, this is clear from this result. Okay. Similarly, in case of germanium, the band gap at temperature T is given as 0.785 minus 2.23 into 10 to the power minus 4 T. Okay. So just like silicon, the band gap of this germanium also depends on T, and with increase in T, it decreases linearly. Okay. But due to this factor of 10 to the power minus 4, you can see this decrement of band gap due to rise in temperature is very small. In practically, we neglect this small decrease in band gap. So in most of the textbook, it is not mentioned that this band gap is temperature dependent, and you get the data directly that this is the band gap of SI, this is the band gap of GE. You read it. Okay. If you are talking about the temperature which is 300 Kelvin, that is at room temperature, then using this formula, you will see that silicon will have a band gap of 1.1 electron volt, and germanium will have a band gap of 0.73 electron volt. Okay. Although at 0 Kelvin temperature, you can see this silicon has a band gap of 1.21 electron volt, not 1.1. And at 0 Kelvin temperature, if you will find the band gap of germanium, what will be this? This will be 0.785 electron volt. When T is 0, this second term will vanish. But at room temperature, this is something smaller than this 0.785 electron volt. This is 0.73 electron volt. Okay. So there is a slight decrement of band gap at room temperature in comparison to the band gap of these semiconductors at 0 Kelvin temperature. Okay. But you can see even at 0 Kelvin temperature, the band gap is not very large. For germanium, it is 0.785 electron volt, and for silicon, it is 1.21 electron volt. In comparison to the insulator, this is much smaller, because in case of insulator, you know, band gap may be 6 electron volt or 7 electron volt. So this much amount of energy may be provided to the electron in valence band by thermal agitation. And so that when you increase the temperature of these semiconductors, or you heat these semiconductors, it is possible that the electrons in valence band will gain thermal energy, and that thermal energy will be greater or equal to Eg, and the electron will move from valence band to the conduction band, and so the material then behaves like a conductor. Okay. Now, as I have told you earlier, that every jump of electron from the conduction band to the valence band creates a hole in the VB. Okay. So the number of electron in CB and number of holes in VB will be always equal. So if Ni is the number of electrons in conduction band and Pi is the number of holes in valence band, then Ni is equal to Pi. And if you consider that these are number of electrons and holes in unit volume, then it is called concentration. This is actually called the intrinsic carrier concentration. So intrinsic carrier concentration of electron and hole in case of pure semiconductor is always equal. Okay. Now, actually, I have written all these facts here. The electrons in conduction band and holes in valence band behave as free carriers. They constitute electric current under an external electric field. But now, let us see the physical condition under which the hole is moving under the electric field in the valence band, and the electron which jumps from valence band to conduction band, which is called free electron, moves under the same electric field. Are the physical conditions same? Answer is no. Electron is moving in conduction band and hole is moving in valence band. Okay? And you have applied an electric field E. Think. Before the jump of electron, there was no electron present in conduction band. But In valence band, the valence band are completely filled with electrons. Okay. Now, if some of the electrons move to the conduction band, then these electrons found themselves in a region which are nearly free from electrons, because in their neighborhood there are no other free electrons. Okay, no other electrons. But in valence band there are so many electrons and so many ion cores. If an electron is released from the silicon or germanium atom, that atom of silicon or germanium becomes ion, positively charged ions. Okay, and that ions also create electric field. Okay, so in valence band there are two fields. One is the external electric field and another is the electric field produced by the ion cores. And these holes move in valence band under the two fields. One is external field E and another is the field produced by the ion cores. Okay, but the electrons moving in conduction band is actually controlled or affected only by the external electric field. So the field under which motion of electron takes place in conduction band and the motion of holes takes place in valence band are different. And that's why so many properties of electron and holes differ from each other, because they are moving under the different physical condition. For example, if you are talking about the effective mass, if you consider that Me star is the effective mass of electron and Mh star is the effective mass of hole, then these two are not equal. Okay. Similarly, if you are talking about the mobility, if mu E is the mobility of electron and mu H is the mobility of hole, these will be not equal. These will be not equal. In fact, it is found that Me star is smaller than Mh star. Okay, and mu E is greater than mu H. Okay, this is all due to the physical condition under which the electron and the holes are moving. Okay, actually all these things I have mentioned here, you can see the conditions for movement of electrons are different from the conditions of movement of holes. The electrons move when the conduction band is nearly empty and the holes move when the valence band is nearly full. Thus, the electron move mainly under the influence of applied field, while the holes move under the combined effect of applied field and the ionic field of the lattice. That's why the properties like effective mass, mobility are different. Okay, so all these things I have mentioned here. Now, as the concentration of whole electron pair increases with increase in temperature, as a result, conductivity increases, and the intrinsic concentration Ni varies with temperature in accordance with this relation. With increase in temperature, you can see from this formula where A naught is a constant, that when T will increase, the number of charge carrier will increase very large, and this is shown in this graphical plot. Now, apart from the creation of electron-hole pair, recombination also takes place, and I have shown it here. Actually, in this case, you can see that if this is your valence band and this is your conduction band, then when electron jumps from this valence band to conduction band, a hole is created here and electron is here. Okay, but at actually in this condition, the hole, the electron moves to the position of hole to complete the bond. So this can be thought like this, that this hole moves from the conduction band to the valence band. This is just like a transition of hole from higher energy level to lower energy level. And so in this recombination process, energy will be released in the form of electromagnetic radiation, and this released energy h nu is equal to Eg. Okay. Actually, if G is the rate of generation of carrier and R is rate of recombination, then these two are equal, and this is given as C equal to Ni times Pi, and this is C into Ni square. Okay, because Ni is equal to Pi. Now we will talk about the Fermi level. Actually, at 0 Kelvin temperature, the Fermi level of this pure semiconductor lies just between the bottom of the conduction band and top of the valence band. Okay, so if EC is the energy of bottom of the conduction band and EV is the energy of top of the conduction band, valence band, then EF is equal to this much. But this Fermi level also depends to some extent on temperature. Okay, on temperature. Because as the temperature increases from 0 Kelvin, then the Fermi level is raised. If you are talking about 300 Kelvin temperature, that is at room temperature, then this Fermi level is raised by 0.01 electron volt, which is actually very small. So practically we say that this Fermi level of pure semiconductor just lies between the valence band and the conduction band, and it is unaffected of temperature. We consider it. Okay, but to some extent it depends on temperature. So if a question is asked like an objective question that Fermi level of pure semiconductor depends on temperature or not, you should answer that this is independent of temperature. So this result we will calculate in our forthcoming lecture when we will talk about the carrier concentration and Fermi level in pure semiconductor, and you will see that this result EF equal to EC plus EV divided by 2 at 0 Kelvin temperature is valid, and it will be valid at 0 Kelvin temperature only when we consider that the effective mass of hole and electron are equal. But in actual sense, MH star is not equal to ME star. So actually at higher temperature, this result is not valid. And we can say that Fermi level then will not lie exactly midway between the valence band and the conduction band. Okay, thank you very much.